Okay, we were talking on Monday. We were talking about solving 3x3 linear systems. What do we mean by 3x3 linear system again? Three variables, three equations. There we go. Okay, so we left off with one like this, right? And remember what our strategy was. When we're algebraically solving a 3x3 linear system, we have to take two different pairs of our original equations and eliminate the same variable. Okay, so we chose the bottom two and we eliminated y, got an equation. Chose the top and the bottom and we got the result 0 equals 25. So what's that tell you about the relationship between the plane corresponding to the top equation and the plane in 3D space corresponding to the bottom equation? Okay, so what's that tell you about the planes then if there's no solution of that partial? Okay, so the planes must be parallel, right? And we looked at a picture and that is in fact what was happening. We had two planes that were parallel and a third plane that cut through those, and so there was no common point on all three planes, right? There was no intersection, so we got no solution. Here's how that might look. It might just be an option where you choose, might look like this, where you would just pick no solution. Or it might look like something like that. You might have apparently more options, but it's still going to be the bottom choice, right? The system is inconsistent. The solution set is the empty set. So depending on how the question is written, you'll see one of those two options, okay? All right, what about one like this, solving a consistent dependent system? So what about something like that? What are we going to do? Look at that for a second and see if, before you do anything, see if you notice anything about that. Well, what do you think? What could we do to solve this system? Ideas. Eliminate y is the idea. Okay, we can eliminate y, that's fine. Top by 3, leave the middle one alone. Okay, let's try that. So I'm going to make this a little bit smaller. Top by 3, we're going to get what? 3x minus 12y. Oh, 9y. Plus 3z equals negative 54. Leave the middle one alone, and what do you notice? Yeah. If I add these up, I just get 0 equals 0. Okay, so what does that tell you about the top two planes? They're the same. Yeah, let's get all the Chromebooks closed up, everybody. Take a look at this. So the top two are the same plane. Okay, another combination of two. What do you think? Probably top and bottom. Make sense? Okay, so what would I do to the top one? Multiply by negative 4. Which is going to give me negative 4x plus 12y minus 4z equals positive 72. Bottom one, if I leave it alone, what do you get? Okay, so I also get 0 equals 0, right? So what's that tell you? Consistent dependent, yeah. So I've got 3. Now, you guys remember from geometry, what was the transitive property? If A equals B and B equals C, then A equals C, right? So we could use, we don't really need that, but we could apply the transitive property here. If we said, we'll just call this equation 1, equation 2, equation 3. If 1 equals 2 and 1 equals 3, then what else has got to be true here? 2 equals 3. I've got 3 planes that are the same plane, so they're all going to overlap completely, right? What would I choose for my answer? Infinitely many solutions, yeah. Okay. All right. Let's see, I want to make sure. Okay. Now notice with that same system, there was another approach we could have taken. If you looked at that middle equation, notice that all the coefficients are divisible by 3. Everybody see that? So I could just multiply that middle equation by negative 1/3, and wouldn't I just get that, right, which is the first plane? And if I multiply the bottom, in the bottom case, all those coefficients are divisible by 4, so if I multiply that one by 1/4, I'd also get that same plane. So I just get the same plane 3 times. There's another way of showing that. Okay, well, how about this one? How about this one? What would I do here? Okay, now, what's your strategy here? Think about this strategically. So we want to eliminate what variable from what 2 equations? Eliminate Z from a combination of A and C. Okay, top and bottom ones, right? And we want to do that because, look, we've got the middle equation doesn't have a Z variable, right? The coefficient is 0. So if we could eliminate Z from equations 1 and 3, then we'd get another equation with only X's and Y's, and we'd have a reduced system there. We'd have a 2-by-2 system with only X's and Y's, right? Okay, so let's try that. So we said the top one we'd multiply by negative 4? Positive 4, right? Because we want to have opposite coefficients, so we'll eliminate the Z term, right? So we'll leave, oops, we'll leave the top one, sorry, we'll leave the bottom one alone, and we'll multiply top one by 4. And what's that give us in the top one then? Minus 16y plus 4z equals 0. Bottom one. So what happens? Everything cancels, right? And I get the result 0 equals 0. So what's that tell us about planes 1 and 3? They're the same plane. Okay. Now, are they the same as plane 2, though? Okay, definitely not, right? Because the second equation is clearly different than the first and the third. So those planes are going to intersect. How are they going to intersect? How do two planes intersect? In the form of what? What does the intersection look like? A line, yeah. Okay, so we're going to end up with how many solutions here? Okay, infinitely many, right? But it's different than this last case. In the last case, we had 3 overlapping planes and we had infinitely many solutions. This is not a overlapping planes, right? We don't have 3 overlapping planes. We only have a line here for our infinite solution set. So we should be able to somehow say something different about this, shouldn't we? Right, because we want to be able to identify that this is different than the previous case where we literally had 3 planes that were exactly the same. So every point in each of those planes represented a solution. Only the points that lie along the line that forms the intersection are going to be the solutions here. So we should be able to distinguish somehow. Okay, how in the world could we do that? What could we say? Well, Here's how we could do this. The variable that we eliminated was z, and so here's how we take care of this in math. And you got to really think about this one, because this one's a little bit, this is going to seem a little strange at first. If the system has infinitely many solutions, write the solution, this is important, write the solution in terms of an arbitrary z. What does that mean? We got to interpret that. What do you think, Cameron?
Is it like you just put like the z that's multiplied by 0?
Not by 0. What does arbitrary mean? We use that word a lot in math. Like if something's arbitrary, just in non-mathematical context, what's arbitrary mean?
It doesn't mean it doesn't like have use or it's like doesn't have
I mean, we're moving in the right direction. I mean, it's kind of. Sometimes we'd call it a dummy variable, so it is sort of like a fake. If something is arbitrary, doesn't that sort of imply that it's random, and that any value? I mean, there's no particular value that we're going to arrive at here. It could be, if we talk about an arbitrary value in math, it means it could be anything. There's no limits, right? So z could be any real number is what that implies. But based on the value of z that we choose for the moment, right, we're going to select a value of z, we want to be able to determine what are the corresponding values of x and y. Now, we do stuff like that all the time. We've done things like that, for example, like if we had a line. Let's just leave that example for a moment, and let's take an easier example that you're familiar with. What if we had something like this, x plus 2y equals 4, and I want you to find a point on that line. What could you do? If I want you to identify a solution to that equation, which would correspond to a point on the graph of that line, how would you do that? I just said, find one for me, please. Okay, so we could say, okay, let's let x equal, take your pick. What's it going to be? 3. Okay, let's let x equal 3. So then if we want to solve for y, what would we get? Well, we just get 3 plus 2y equals 4, right? And what's y? Well, I mean, if I solve for y there, what am I going to get? 1/2. 1/2, right? Everybody get that? Because I'm just going to get 3 plus 6 equals 4. Actually, wouldn't it be? No, you're right. 2y plus 3 equals 4. So if I subtract the 3, I get a 1 on that side. Yeah, 1/2, right? Okay, another way of saying that is we could, if I were to solve this for y, wouldn't y just equal 4 minus x over 2? I could use that algorithm to quickly plug in any value of x and find the corresponding y value, right? So I'm just picking arbitrary values of x and solving for y. There's one I picked. I just arbitrarily picked 3 out of the blue. What if we pick x equals 14? Well, 10 minus 14 is negative 10 over 2. Then that tells us y equals negative 5. We do it all the time. We pick arbitrary values of one variable on a line and we solve for the other variable to find a solution, right? Okay, give me thumbs on that idea. Like you've actually done this without using that terminology, right? Pick an arbitrary value, plug it in to find the other variable. Okay, well that's what we're going to do here. We're going to pick an arbitrary value of z, and then we'll just figure out what the values of x and y are, you know, in terms of that z, right? What does that middle equation tell us? X plus y equals 0. Well, this is the same thing as saying, if I solve for y, for example, this just tells us y equals negative x. Everybody see that? Okay, so if I know that y is always going to equal negative x, because our solutions are going to fall along, they have to, any solution that we get from this system has to satisfy that middle equation, right? So I know that always y is going to have to equal negative x because that has to be true. Okay, so if I plug that in for my y value there, what do I get? 3x minus 4 times negative x plus z equals 0. Well, that's 7x plus z equals 0. In other words, if I isolate x here, 7x equals negative z, divide by 7, and I get the result x equals negative z over 7. I can pick any value I want for z, plug it in, and I'm going to be able to compute the corresponding value of x for that solution, just like we did with a two-dimensional line, right? I can do the same thing for y. I could do the very same thing for y. I know that if y is equal to negative x, then what's going to be the value of y in terms of z? Y equals negative x, right? Well, what's x? Negative z over 7. So y equals z over 7. So now I know the value of x in terms of z. I know the value of y in terms of z. And z is just going to be is a variable whose value we're just going to randomly select. So I could write then my solution like this. I could write my solution as the ordered triple negative z over 7 positive z over 7 is my y value, z. So what if I pick z equals 0? What's going to be a point in three-dimensional space that lies on our solution? Yeah, I'd get 0, 0, 0, right? What if I pick z equals 1? What's going to be, because remember our solution we're talking about is just going to be a line where those planes intersect. I'm just trying to find some points on that line so I can visualize what the solution set looks like. What if I pick z equals 1? What point do I get? Negative 1/7, positive 1/7, 1. If I pick 7, I'd get negative 1, positive 1/7. Everybody see that? Okay. That's a little, I mean, that's when it's new. You don't really have a lot of prior experience to connect that to, so that's when you got to think about it a little bit. But what'll help is let's look at the solution. I think this will really help you conceptualize this. Again, for your notes, here's what we did, right? We decided that equations 1 and 3 were the same thing, so they represent the same plane. And because x equals negative y, we're able to solve for y in terms of z and therefore x in terms of z, right? Okay, so that's what we did. Just that'll be there for your notes. Now let's look at this. I know I made a graph of this. Where'd it go? Oh, here it is. Oh, how would we input our answer down here real quick? Which A, B, or C, which one would be the correct choice? Which one? B, yeah, okay, it's going to be B. Right, we're going to choose B. And how would I fill this in? If Z is arbitrary, what would go in these two boxes? Yeah, negative 1/7 Z and 1/7 C, right? Where was our, I can't remember which one was, oh, here it is. X is negative 1/7 Z, so it would look like this, right? Just like we had before. Was X positive or negative? I can't remember. Negative, yeah. That's our solution set, would just be all the points that follow that pattern where I pick Z randomly. Z, an infinite number of values I could pick for Z. Okay, so what does this thing look like? Okay, let's stack up our planes. There was the, was that our system? Was that top? It looks different. Maybe I'm. Okay, yeah, this one's. Okay, I picked one. I don't know why. This one's a little bit. I don't know why I picked a different equations, but they're all equivalent. Just trust me on that. I don't know why I wrote those down as different equations. But that's what our first plane looks like. That's what our third plane looks like. So they overlap, right, perfectly. And then that middle plane is a different one, and we're just looking for, you know, the solutions that lie along that line. Okay, well, watch what happens here. If we pick if I pick ordered triples of the form negative, I chose A instead of Z because I can't use Z in this case. Desmos won't let me. Negative, pretend that A is a Z. Negative Z over 7, Z over 7, Z. Look what I notice. Right? That's a point that's on the intersection of those two planes. Now watch what happens if I just vary the value of A. Look what it does. Which is really Z, right? As I vary the arbitrary value of Z, I'm just getting points that lie along that intersection then, right? Because they all have to fit that pattern. Thank you. Okay, does that make sense? Okay. All right. I can even set that thing in motion there, and you can see that that point is just gonna always stay on that line. All right, I think we're pretty good here. I'm gonna turn you loose. Enough already. You can work on the assignment. Have at it. Yeah, you bet.